Okay, so first question, quite easy. They're asking for the standard deviation and the mean. So this thing over here, the sum of the x values is for mean, right? So you're going to do x bar, which is the sum of x over n. So that should hopefully be quite easy. So this is not a difficult question. Please remember that we don't round off our mean at all, right? So it's done. Then standard deviation. So we have got the x squared. So every single time you see x squared, you're going to think standard deviation. That's what we need it for, the sum of the x values. We've got the mean, we've got everything. So hopefully that's a relatively easy question. So you're just going to put this inside here. Whoops. Don't forget to square the mean. You should recognize if your answer is rubbish, because if it is, like this is talking about the amount spent. And, you know, if your answer turns out to be that the person is spending $20,000 every week on shopping, something is wrong, right? So pay attention to your answer. Your standard deviation should be something small. Okay, so here's the mean. So you obviously have the equivalent of 18 people who got 30 marks each. So that's literally 30 plus 30 plus 30 plus 30 plus 30, 18 times. And you have 12 people who got the equivalent of 28 marks each. And that adds up to a total of 30 people. So your mean is going to be 29.2. So if you look at our formula, we have got the mean. There it is. We want to find the standard deviation. We've got the total sample size. It is 30. And what we want is the sum of x squared for the two groups together. And as I've just said to the rest of the class, the only way to do that is to find the sum of x squared for the two groups separately and then to add them. Remember, you cannot get from the sum of x to the sum of x squared ever, so we'll have to find the sum of x squared. Give some thought as to how you think. Okay, so we're going to work out use the standard deviation for each one individually and work out the sum of x squared. So if you think about it, they've told you what n is individually. So there it is, you know what n is. You know what the mean is for the individual group, right? And in addition, you know what the standard deviation is for each group. So then you can solve for the sum of x squared. So you can either solve the equation for it each time, which is what I do, or you can memorize the formula, which is risky if you get it wrong, right? But basically, if I want to solve for x squared, then I'm going to square for both sides. So I'm going to have the standard deviation squared, which remember is the variance. And then I'll have that, right? And then I'm going to have the standard deviation plus the mean. Let me not drop the bar. Is equal to the sum of x squared over n. And so if I want the sum of x squared, that is going to be n times by the standard deviation squared plus the mean squared. Okay, so then I would do it for each one of these two things separately. So for the girls, I'm going to say for the girls, sum of x squared, n is equal to 18. Standard deviation is 2.5, which is squaring, and x bar, which is your mean, is 30. And then for the boys, I'm going to do that separately. So there's the boys, so this is girls. This is boys. Same thing. For the boys, we have 12 of them. Their standard deviation is 3.1. Their mean is 28. And solve. So that should be a relatively easy thing for you to do, hopefully. And you are going to get, I'm just looking for the answers, you're going to get 9,523.32. Please check that you do. And the other one is going to be 16,312.5. And that adds up to a combined x squared of 25,800 and looks like 35 and 82, right? And that is now what we're going to put back in here and you'll be able to work out your standard deviation, right? Which I'll do in a minute. So, looking over here, that is our final answer. So the combined standard deviation, you've got the combined x squared value, and then divided by 30, because the sample's 30, minus the mean that you worked out. Round off everything to 3 significant figures, work with 100% accuracy throughout. So, coding. They are taking a certain amount away from each data point. So every single data point, they've decided, so this is the example on page 21, they've decided to take 340 mils of Coke or whatever it is away from each and every single can. And the advantage of them doing this is bloody annoying actually, but the advantage of them doing it in real life is you can work with very simple data. So if the average thing is 1,156,000 and everything is either 3 or 4 units above or below it, we can just take away 1,156,000 and work with these tiny numbers and not have to work with these massive numbers, which before computers was very valuable. Now it's considerably less valuable, but they like this question. You're going to see it for sure. Okay? So just to give you a sense of what they're doing is, say we had 3 cans. The one was 344. You'd be going 344 minus 340, and that would be 4 milliliters. Then you go 336 minus 340. That is what they are literally doing every single time, and that's going to give us minus 4. And you'd go 328 minus 340, and that's going to give us minus 12. So when they've added them up, they've literally added those numbers up once they've removed 340 from every single one of them. So this one is going to end up as minus 12, right? Once you've got that information, you can work backwards and you can find the mean of the original sample, okay? Because if we have 3 of these here, the mean of this sample, so the mean of the adjusted sample, is going to be minus 12, because that's all the numbers added up. And obviously there are 3 cans in my little example, so the mean is going to be minus 4. So that means on average, once we've subtracted the actual mean, if we took away from 340, we'd get minus 4. Do you get that? So the actual mean, if we had the mean and we took away 340, we would end up with minus 4. I'm sorry, I keep on making it degrees for some reason that I'm not sure why. We would end up with minus 4, because that's what we've done, isn't it? We've worked out the mean for them. It turned out to be minus 4, which means on average these things are really 336. So 336 minus 340 is going to give us the minus 4. We have the actual mean of the actual sample, and the actual mean is 336. So maybe write that down, and then we'll carry. So this is just an example. Your actual question is this question here. Your actual question, it says, once we've taken x minus 340 of 50 of them, we end up with minus 200. If I wanted to know the mean for that sample after the adjustment's been made, I'm going to say minus 200 divided by 50, obviously. I've added them all up. I'm going to divide by 50, and I get minus 4. And so the mean for this question is 336 for the same reason, right? You've taken the mean, the average, you've subtracted 340, you've got minus 4, so the average is 336. Okay, so the idea behind the standard deviation, look at my little drawing. So these things over here are the original points, the actual amounts inside those cans, right? So this one might be 348, and this one might be 340, and that one's 336, it's the mean, and this one might be 328, and this one might be 320, say, right? If you take 340 away from each of them, you're going to get exactly the same distribution. Do you see that the pattern of how they spread out is the same, right? If you take 340 off them, they're all going to move the same amount. You'll get exactly the same pattern. The standard deviation is the pattern. It's how they are spread out around the mean, right? So the pattern is the same. So the important thing here is that the standard deviation for the coded sample is equal to the standard deviation for the original sample. So for the original sample, we don't have much information. We know that there are 50 cans. We could fill this in. Sorry, I've left out the square. We could fill in that. And we could fill in that because we've worked out the mean, okay? But we could not actually fill in the sum of the x squared values because we don't have them. But we do have them, if you look at your notes, we have them for the sample. If you work out the standard deviation for the sample, you will have the standard deviation for both, right? Because it's exactly the same. So it says that the sum of x minus 340 squared is 962. We know that there are 50 cans in our coded sample as well. And we know what the mean is in our coded sample because we worked it out as part of working out the mean for the other one. It was -4. So this is going to be minus, let me just put this in accurately. It's going to be minus 4 squared, right? That's your standard deviation. That's as simple as it is. Once you have worked out the mean, the hard piece is finished. So this is going to be a standard deviation of 1.8.